But mostly for architecture purpose, increasing mass doesn't really matter, right? Doesn't really matter the performance of room or the building. We can just put one more layer of bricks that will reduce transmission, increase the transmission loss 6 dB, right? Or we can use a stiffener to stiffen the wall, and we can also increase the transmission loss. But if you decide to use, for example, some gypsum board, okay, or in Korean, benidapan, the first thing you have to know is what is natural frequency is. Okay? Okay? And then you have to know the frequency that you want to control, where it is. If the frequency that you want to control is well above, in other words, more than 1 octave of the natural frequency, then you can conveniently or safely use the mass law. And then what you do, you just determine the blocked frequency and then obey the mass law, that is 6 dB per octave things, and then you can easily determine the thickness of the partition that will give you the desirable transmission loss. Okay, that is related with the problem you had in the midterm examination. Okay? If the natural frequency of the board you selected is well above the frequency that you want to control the sound, then what you have to do? You have to follow the stiffness control rule. That simply means that if you increase the S twice, then you will have 6 dB sound reduction too. But increasing stiffness, it's not easy. Increasing stiffness normally shift the natural frequency of the partition too. Which way? This way? No, this way. So what you estimated by just using stiffness control reason concept is a safe decision. Is a safe reason, meaning that what you guess using that formula, this formula, over-predict what you really get. So it's a safe. Right? If you add mass, then the natural frequency will shift down. So if using mass law concept is a safe disease, safe way for engineering. So in both ways, it's safe. Right? And also we are using dB scale. We don't care about the error factor of 2, right, in magnitude. Because that is 3 dB. Right? The difference between 10 dB and 3 dB is not just 3 times. What's the difference between 10 dB and 3 dB? In power sense is the difference of 10 to the 7. So if you add 3 dB sound to the 10 dB sound, what you will get? 동수. 10 dB, right? 3 dB is nothing. So don't afraid of making error, magnitude of 2 error in using, in controlling or in designing partition. Because that is So trivial. So mass law is very powerful. Mass law is very powerful. We normally use mass law for designing partition. That is our conclusion. Right? So the number you have to remember is what? 132. Doesn't matter it's 132 or 130 or 100 even. Right? Because the business we are handling is first is in dB scale, and also the characteristics of this curve is likely provide us to have a safe design. So this is a very convenient tool to design the partition. Okay? So as a conclusion, what is our conclusion? Oh, mass law is so wonderful. That is our conclusion, right? How to use mass law? What is the flag frequency that determines whether or not we can use mass law or stiffness law? It's natural frequency of partition, right? If the frequency we have to control is well above the natural frequency, we use mass law. If that is well below the natural frequency, we use a stiffness control concept. Okay? And the text provide you the detailed procedure to derive the result and so on. Okay? Next lecture we will talk about the case when we have this kind of plate and when we have incident wave has this direction. What if we have the wave not coming normal to the surface but obliquely to the surface? Conclusion? Simple. The only change is partition impedance, and the same concept holds. And also, if the wave come in obliquely, then the result, transmission, if we design the partition using the transmission loss based on normal instance, again, that is safe design. Safe design. So, we likely finish to study chapter 3. But there is some objection, so I will continue to talk about the chapter 3 in the next lecture. Okay? So see you on coming Thursday.